Okay, the synchronous generator operating actually can operate alone. That means each synchronous generator can be connected to the load to supply a specific load as a standalone unit, or can be operate together with other synchronous generator, and we call it the work in parallel with other synchronous generator when they connect it to the grid. Okay, so the behavior of synchronous generator under the load when we is connected alone to the load, okay, it depends on the power factor of the load. So when we set the power factor, since the synchronous generator used to provide power, or the output of synchronous generator is electrical power, and this electrical power we said equal to say 3 v line uh, I terminal or I line cosine theta, or the power factor. So the value of the power factor of the load will affect the behavior of the synchronous generator. So this power factor has three cases: either lagging or leading or is equal to 1. So the lagging if our load is inductive load, the leading if our load is capacitive load, and the 1 value when our load is resistive load. Okay. Although most of the synchronous generator actually are connected or working as a part of the electrical power system, so they are working in parallel. That means not working alone, but also we still have some synchronous generator which working alone or in island mode to supply some specific load. So as you can see here, this the when the system or the synchronous generator is operate alone. So the generator is connected directly to the load here, and we see the power factor will affect the behavior of the, or the power factor of the load will affect the behavior of the synchronous generator in this case. So we have when we connect it to the load, the resistor of the field resistor of the generator will not be changed. So the magnetic flux or the field current or the that will be produced in the rotor or in the field winding of the synchronous generator will be constant and unchanged. Also, the speed of the synchronous generator, we said since we call it synchronous generator, so it has only one speed, which is the synchronous speed, or which equal to the machine speed, and this speed actually is constant based on the uh, or for all conditions from no load to the full load. So also the voltage or the internal voltage, which is EA value here, is also constant for when the operation or the generator is operate in the alone or standalone operation mode. So when we assume that the power factor here is the power factor of the load change or is fixed or constant, that means no change. We said either power factor is lagging or leading or equal to 1 for resistive load. If the power factor is fixed or constant, that means the value of the current here will be changed based on the load. So when we increase the load of that connected to the synchronous generator, it will takes more IA, more armature current. Okay, when we increase the load, the value of armature current will be increased, while the other value here for the armature or the internal voltage, we said it's constant, and terminal voltage will be constant. So the voltage drop across the synchronous reactance, which we call it here the armature reaction voltage, which is JXA XSIA, will be changed. Okay, so the armature reaction voltage here factor will move parallel to its initial condition. Why? Because we have this is constant, EA V phase is constant. When we increase our load, only the value of GXSIA will be changed. By increasing the load in the stand-alone operation mode or in the of synchronous generator, only the value of IA will be changed, and this will cause the value of or the voltage drop of that we call it reaction voltage will be changed. Actually, here we can see the effect of the changing the power factor, and not we who will change the power factor. The power factor will be changed based on the connected load to the nature of the connected load to the synchronous generator. And we said if our load is inductive load, so the power factor will be lagging, and this will make the voltage decrease significantly. So when I connect inductive load to the synchronous generator, the terminal voltage of the synchronous generator will be decreased significantly. So it will cause voltage drop, okay, if the load is inductive or lagging load. If the power factor is unity, that means our load is pure resistive load. So in this case, the value of cosine theta is equal to 1, and the phase or the terminal voltage of the synchronous generator will be decreased but slightly. So this will be actually the ideal case that we have a resistive load only. If we have a power factor leading, that means we have a capacitive load. And if we have a capacitive load, the capacitor is going to provide more voltage to the grid or to the network, okay, to the system. The capacitor usually provide voltage. Since it will provide voltage, it will cause the voltage to rise. Instead of decrease in the first case, it will be increase in this case, okay. So the voltage in that case, when the capacitive load is there, the voltage will be increased. For that, usually they use to connect some capacitive load to the grid in order to improve the voltage during the peak time. So if there is a voltage drop in the or a lot or a big load is connected to the grid, which cause voltage to be dropped due to the some inductive load, we are going to add capacitive load in order to uh, increase the voltage of the system. Okay. So as we said before, we have reactive power, which is Q. So we have positive reactive power, Q, and negative reactive power, Q. So the positive reactive power is generated from the lagging or inductive load. The negative is generated from the leading or the capacitive load. And usually, if we have lagging, if we have inductive and capacitive load, it will be neutralized. So if we have plus 5 kilovar, for example, and minus 5 kilovar, it's equivalent to if we do not have any inductive or capacitive load, because plus 5 minus 5 it will be 0. So in this case, our system will work or behave as if it has unity power factor. So in order to improve the power factor, we need to make the power factor equal to 1, and this can be done by connecting capacitive load to the system. So the capacitive load will be decrease the impact of the inductive load, which decrease the voltage in the network or in the system. Okay, effect of the load here. The change of in the load from inductive to capacitive and so on, or the value of inductive load from no load to full load can be measured by determine or calculate the value of voltage regulation. And this voltage regulation we already mentioned before in the transformer. So we said the voltage regulation here is equal to V no load minus V full load over V full load. So we are going to find what is the voltage of the generator in the case of no load is connected, and what is the voltage of the generator in the case of full load is connected, and divide by the full load value. So it will be like a ratio. So in if the V no load equal to the V full load, so the voltage regulator is equal to 0. So this is the ideal case. If the V no load is higher than the V full load, so that means it will be positive. The voltage regulation is positive, and this is the worst case or the bad case. And if no load is less than the full load, that means the value or the voltage regulator in this case will be negative value, and this is it means that there is a capacitive load which provide or increase the voltage of the system. We said that usually the synchronous generator are operate in parallel. So the parallel operation of synchronous generator is the most common case of operation mode of synchronous generator. and actually it has obvious advantage over the alone operation. Okay, some of the advantage of parallel operation of synchronous generator, actually several, when we have several generator, it can supply bigger load. So instead of have one generator only, we have three generator connected together, so it can supply higher or bigger load at the same time. Failure of a single generator does not result in total power loss. If I have only one generator and it's fail or is shut down, so I cannot supply the load. But if I have two or three generators, if one of them is shut down, the other can still supply the existing load. Individual generator may be removed from the power system for maintenance. So if I have several generator connected in parallel, and one of these generator need to do or to go under maintenance, so I can stop one of these generator and the other generator continue to supply the load. Single generator also not operating at near full load may be quite inefficient. So actually when I run single generator and in order to I mean, if I have several generator connected together, I can run this generator not at the maximum power. I can run them at the value near to the full load, so their efficiency will be much better than if they run at low load. Low load or maximum load. These are the advantage actually of parallel operation of single generator, and you need to know these points. So this when we compare the parallel operation to the alone operation of synchronous generators, there are some conditions need to be satisfied in order to allow the parallel operation of synchronous generator. So it's not easy to connect two generators together. It's not just randomly. If I have two generator, I can connect them directly. No, there are some conditions need to be satisfied in order to connect more than one generator. So this condition actually, if it's not satisfied, it will cause problem or it will cause a fault or circulating current between the generator, and this may damage or cause damage for the generator. So these are the conditions that we need to, or that the synchronous generator need to satisfy in order to connect two generator, three generator, five generator, whatever is the number of generator in parallel. The first one is the RMS line voltage of the two generator must be equal. So when I connect generator one to generator two, so these two generators, I want to connect them. I cannot connect them directly. No, the first one, the voltage of each generator should be, of both generators should be equal to each other. Okay, so the RMS voltage of generator one must be equal to the RMS voltage of generator two. Okay, the second is the generator must have the same phase sequence. When I say phase sequence, that means the phase A, the first generator has phase A, B, C. That one has the A prime, B prime, C prime. So it cannot be A, B, C, and this one A, C, B. Should be the same sequence. I have first phase A, the first phase A, second B, second B, third C, third C, and so on. Okay. Then the angle between the two A phase must be equal. So if I set the angle, usually we said if we have three phase, that means there is angle difference between, or phase difference between each phase to other phase, which equal to 120. Since the total cycle is 360 degree and we have three phase, the angle between that each two phase is equal to 120. So if the angle of the phase A is 0, the angle of the phase A in that second generator also must be 0, cannot be 120. B is 120, B 120, C is 360, C is 360, and so on. Okay, 240 and 240. So this will be the the phase angle of the two A phase must be equal. Then the last is the frequency. So the frequency of the generator one must be equal to the frequency of generator two. And when I have a grid and I want to engage one generator to the grid, this frequency it's preferred to have higher frequency than the grid frequency, because the lower frequency will cause the current to go through the from the grid to the generator and cause the reverse power. So these are the conditions that must be satisfied in order to operate two generators or two synchronous generators in parallel. So if we have a large power system here, that means we have a grid, not only two generator. We have electrical power system which consists of many synchronous generator, and they want to add one generator to this grid. So the frequency and terminal voltage of the generator usually are controlled by the grid, not by the generator itself. So for example, if I have the frequency of this generator is 50 hertz, and I connect it to the grid which has frequency of 49.9, so the frequency of the new connected generator will be 49.9, okay, or it will be the same frequency of the grid. I mean, usually when we add the generator to the grid, its frequency and its voltage will be controlled by the grid itself, not by the generator itself, okay. So the governor here of the generator will be uh, control the real power generated by the generator. For example, I have generator is 5 megawatt. So in order to achieve the 5 megawatt, the generator here, the generator of the or the governor of the generator will increase the load of this generator. The second is the field current of the generator will control the reactive power. So we have, in order, since I connect this single generator into the grid, which consists of many other generator connected together, so the governor will control the real power, and the exciter or the field will control the reactive power. So when I connect my generator to the grid, it has two type of power: real power, which is P, and reactive power, which is Q. The real power is controlled by the governor of the generator, which control the torque of or input to the generator, or the mechanical power input to the generator, and field current, which or the excitation system, which control the voltage and at the same time will control the reactive power of the generator. So if you have the, for example, if we have two generator connected in parallel to feed the load here, so these two generators should distribute the load. So for example, if the two generators are equal to each other, so this one is 5 megawatt, this one is 5 megawatt, and my load is 8 megawatt. So each generator should take 4. So it will divide the load depends on their capacity or in their on their power. So if the generator are equal, they will divide the load equally. If the generator 1 is greater than generator 2, generator 1 will carry higher power than generator 2. If the generator 1 is smaller than generator 2, it will take lower power value than the generator 2, either for the real power or the reactive power. So we can see here the total power or the load power will be divided by power of generator 1 plus the power of generator 2. So the load will control the power taken from each generator. The value of the load will control the power taken from the generator. When we say the loads, means the loads that we connect to the generator, like the light, like the motors, like bridge, any other equipments, any load connected to the or some for factory, or for example machines, process which connected to the generator here, it will control how many the power or the active power from generator 1, how many the active power from generator 2, how many the reactive power from generator 1, and the reactive power from the generator